Hello everyone. In this video we are going to talk about elasticity, and we will start with the concept of elasticity, elastic and plastic regions, Hooke's law, types of stress, Young's modulus, shear modulus, Box's modulus, and ultimate strength of materials and fracture. So let's begin with explaining the elasticity, what elasticity means. Well, in simple words, elasticity is the property of materials when forces are applied on those materials undergo deformation. But this deformation is temporary. It means that when the forces are not too great to cause fracture or permanent deformation, if the forces are not too great, material can get back to their previous shapes and sizes when the forces are removed. So this property is called elasticity, and it is in all materials. In some materials, that is very obvious, for example, rubber bands or springs, but in other materials is not visible and is not tangible. This graph, which is known as force and elongation graph, or sometimes in some resources or some books or textbooks, is written as stress and strain graph. That shows the elastic and plastic regions of the materials. That's a very important graph. So in this graph, as it illustrates, we see there is a linear region, this linear region. So this linear region means that the force is directly proportional to elongation or change of the length or sizes of the material. That means that if the force in this area, in this region, applies proportional, it causes proportional elongation or change in length of the material. But when the forces or force or a force is removed or they are removed, then the material can get back to their previous shapes and size. So this linear region means elastic region, but it has elastic limit. So this force, if we increase the force until this point, elongation or the change in length or size will be directly proportional to the force. But then if we exceed this area, if we increase the force even further, what will happen? We will enter the plastic region of the material. It means that then the elongation is no longer linear, proportional in a linear way with the force. So as you see, if we apply a little bit more force, let's say F prime, and you see the elongation will be much greater than the amount of increase in force. So that means they are not proportional in a linear way. And even if we increase the force further, again, this will continue to reach the breaking point or ultimate strength of the material, and then after that it will break, or it will yeah, it will break. So in this area, let me erase it and then mark it clearly. So in this area, the linear area, the deformation of the object which is caused by the forces applying on that is temporary. It means that the forces, when the forces are removed, they will get back to their previous shapes and size. But in this area, plastic region, the deformation is permanent. It means that even if we remove the forces, the object will not, or the material will not get back to their previous size or shape. Now, let's see what Hooke's law says. So in this lesson, we are focusing and we are talking about this linear region. So all we are going modulus that we are going to talk about all are in this linear region or elastic region. And then at the end we will talk about this fracture or ultimate strength of material. So the first law that we are going to talk about is Hooke's law. So Hooke's law simply explains that suppose we have a spring which is fixed, one side is fixed to the stable object or wall, then this spring has a length, and if we apply a force on this spring, the length will increase. So this increase or elongation is shown here by x. So suppose we have we apply 1 Newton force, okay, on this spring, and then this spring will elongate, or it will increase its length by some amount. Then if we double the force, we will see the elongation or the deformation or the increase in the length will increase by 2 times. And if we keep increasing this force as much as we are still in this elastic region, this linear region, we will see the reaction of this material, this spring will be again the same. So then if we divide the force by the elongation, we will see that we will get the same number. So this number in this fraction will be the same as this, will be the same as this. So then this number is constant, and this number is called the constant of spring, or we show it by K. So this K is the constant of spring. So Hooke's law says that the force applied to a solid is proportional to the extension produced. This principle is known as Hooke's law. So this force is external because we apply force from outside. And but sometimes we see the Hooke's law by a negative, and this negative is because it is about, this equation is about the internal or spring force, not the force that we are applying from outside, external force. Because when we apply a force, the spring also applies the force in the opposite direction, and the direction of this force is opposite to the direction of the uh, displacement that this spring makes. So therefore, the directions are opposite. Therefore, we have a negative here. So this F is uh, internal F, or F applied by the spring. Whereas in this equation, the force that we apply from outside, or external force applied on the spring. Now we will move on to two important concepts or terms, which are stress and strain. So stress is simply defined as force per area, and this means this is similar to the concept of pressure, and the unit for stress is Pascal. Okay, and how about the strain? Strain is the ratio of the change in length to the original length. So original length of the material or the object is shown by L sub naught, or is denoted by L sub naught, and delta means change. Delta means the displacement or the change in the size that material will experience after a force is applied on the material. And these are the definitions of stress and strain. So stress is the force per unit area within a body. In fact, it is a measure of the strength of the agent that is causing the formation of a body. Stress is applied to the material by external agents. And also strain is the fractional deformation of a body resulting from a stress. It is measured by the ratio of change in some dimension of a body to the original dimension in which the change occurred. Strain is the material's response to stress. So this is a very important concept. Strain is the material's response to the stress. And strain does not have any unit. It has no unit. No unit. And the reason is because this is meter and the other one is meter also. So meter with meter, they will cancel out each other. So there is no unit for strain. And now Young's modulus. Young's modulus is also known as tensile modulus. It describes the length elasticity of material. We described stress and strain in a general form, but in this context, they are known as tensile stress and tensile strain because Young's modulus is about length elasticity of material. So Young's modulus is the ratio of the stress to strain, as you see in this equation, and it is denoted, or it is shown by capital letter Y. The unit for Young's modulus is again Newton per square meter because strain, as we said, has no unit. It's just a number. So L, again, in this part, L is the original length of the object. A is cross-sectional area, and delta L, which is the change in the length. So here we are talking about the length due to the applied force, and y, or capital letter y, is Young's modulus, which is the constant elastic number. So there is a table which shows the the constant of proportionality, or um, modulus of different materials. As you see, different materials here: iron, steel, brass, aluminum, and so on. So they have all been tested and measured, and they have a specific number for the tensile, for example, elasticity. So this column is showing the Young's modulus number for each. Yeah. So in this textbook, or in this resource, Young's modulus is shown by E. So sometimes in some references it is also shown or denoted by E, but most commonly it is shown by Y, because it comes from the first letter of the Young's modulus. So change of the size of the material is not always in a tensile form. So it's not, the stress is not always tension or tensile. It's sometimes about compressive. It's sometimes in compressive way, and also in a shear form way. So sometimes we have compressive stress, which this also will fall into the context of Young's modulus, because again we will see the change in the length. So change in the length is not an increase. In this case, it is a decrease of the length. So delta L here is known as the change caused by compressive stress. But how about shear stress? What is shear stress? So sometimes the force is tangent, applied in a tangent way, as you see here in the picture, in the photograph here. Force is tangent to the surface. So then the deformation is like in this form, as you see. So therefore, in this context, we are going to talk about shear modulus, because it's no longer about the decrease or increase in the length. As you see, the object has undergone the deformation in this form. So as you see, it's no longer about the deformation of the length, as in a different form of deformation, as you see in this image here. So again, in shear modulus, we have shearing stress and we have shearing strain. So shearing stress, again, the definition is the same thing as that of in Young's modulus: force divided by surface area, cross-sectional surface area, but surface area of this area, the area that the force is applied and the force is tangent. And shearing strain can be also the ratio of delta L by divided by L, by the size, and also this length, delta L divided by this. And also sometimes is shear shearing strain is shown by phi, which is in radians, is measured in radians. So again, we have the same equations that we had in Young's modulus. Again, shearing stress, but here shearing strain. And the force which is applied on the object is quite different from that of Young's modulus. So sometimes this phi, which is in radians, measured in radians, as you remember, if we have such a case, which we need to measure the length of the arc, which in this case, let's say delta L will be equal to L times phi. And then if we solve it for phi will be equal to, again, delta L divided by L, which is the same concept. So therefore, shearing strain and sometimes is shown by phi. And the last modulus, it's Bulk's modulus. Bulk's modulus is used to measure how incompressible a solid is. So when we talk about incompressible a solid is, this falls into the context of Bulk's modulus. Again, we have the same concept. So we have a modulus, we have a number that we talked about in this column, in this table, Bulk's modulus. The unit is Newton per square meter, and for each material is different. Yes, and but the thing, and also the Bulk's modulus is equal to stress divided by strain. So here we have we are talking about volumes, so therefore volumes, instead of changing length or the shear way of change of the object, we are talking about the change of the volume, because the object is under the pressure from all possible sides. For example, when suppose you submerge an object in the water, so that object is experiencing the pressure from all sides. It's not all about one side. So therefore, the volume will change. The volume of the object will change. Therefore, the strain here is defined as delta V over V sub naught, which is the first volume, the original volume, and here delta V will show the change in the volume. But we have here negative sign, and that negative sign is because the volume always shrinks, so the volume will always decrease. Therefore, it's smaller than the previous one. Therefore, we need to show it by a negative or minus sign. There is another difference from this Bulk's modulus with the two other moduli, and that is, here stress is a little bit different, and the stress we see is shown by delta P, and delta P is the change in pressure. And what does that mean, the change in pressure? So to simplify this concept, change in pressure, and how to calculate that, we need to consider all the objects in the air. Now they are under pressure, air pressure. So when we submerge it into the water, suppose we have two medium, here is air and here is water. Each, they have their own pressure. So all objects in the air, suppose this is a cubic. So therefore, this is under the air pressure. So there is a pressure acting on it. So P sub naught, for example. And then when it is submerged into the water, so therefore again a different pressure will be acting on it. So it will be let's say P. So therefore this change is shown by delta P. So here a stress, and we call it stress in the concept of Bog's modulus. The stress here is quite different from those previous moduli that we studied. And the last one is about the fracture. Uh, what does that mean, fracture? So if the force which is applied on the object is too much, it will cause fracture. And also it is measured and shown in a table, as you see here, which different objects, they have different uh, tensile strength, which is about ultimate strength of the material, the point that they will break or they will fracture. And so as you see, different materials have different ultimate strength points that they have been measured and they have been presented in this table. So you can find it in different textbooks of physics or in other different references. Okay, so that is the end of our lesson today.